we take a block that has 3 kilograms and we push it from rest. We push on it with a constant force, a distance of 3 meters. And then we stop pushing. And we find that that block, as a result, is moving at 20 meters per second. It then collides with a much larger block of 12 kilograms. And right after that block, there's a rough section of track that has a coefficient of kinetic friction of 0.2. Now, remember, we're always deciding, is this energy or is this momentum? The first part of the problem asks, what's that normal force by the hand on the block? How big is that force? Now, the decision tree is as follows. The first question we ask ourselves is this a collision? Well, yeah, it's going to collide in a minute, but it hasn't yet. Now, if it's a collision, that's a momentum problem. But it's not a collision. The second question we ask ourselves is time involved? Are we calculating time? Are we using time? If so, it's a momentum problem. But no, it's not time that's involved, it's distance. We're pushing for 3 meters. So if it's not one of those first two, it's likely an energy problem. And so I'm going to use energy. And to use energy, I always start with this equation here, energy initial. Let's put that down here. Energy initial is equal to energy final, except when it's not, and it's not when there's external variable. Now, the next step after I've written that equation is to identify what I mean by the initial state and the final state. Well, I'm trying to find out how hard this hand is pushing for the 3 meters. So I better put my initial at the beginning of those 3 meters and my final after those 3 meters. Now, at each of those events, I ask the same three questions. Right here, right at the start, is anything with mass moving? Not yet. Is anything up off the floor? No. Any spring, stretch, or compress? No. So the energy initially is 0. Then I go to the final event and I ask, is anything with mass moving? Yes. So I have kinetic energy. Is anything up off the floor? No. Any springs stretched or compressed? No. Okay. Now I notice that this is not the same as that, and that's because the hand does positive there, force times the distance. And so if I start plugging in what I know, the only unknown is the hand on the block. I multiply that by 3 meters and I get 1/2 times 3 kilograms times 20 meters per second squared. Now this means that the normal by the hand times 3 meters is equal to 600 joules, and that's going to give me the normal by the hand on the block is 200 newtons. Okay? See how easy that is? Then the little block slams into the big block, and we're told that after the collision, the little block stops. And the big block takes off. And the first thing I want to know is how fast is that big block going right after the collision? Well, that's, because it's a collision, that's a momentum problem. I conserve momentum, and I need a coordinate system with momentum. Now, before the collision, I had 3 kilograms moving at 20 meters per second to the right. That's positive momentum. I had 12 kilograms not moving at all. You see how I just wasted ink? After the collision, I had the 3 kilogram block not moving. I just wasted some more ink. And I had the 12 kilogram block moving, speed I don't know. But I know the direction it better be to the right. Okay? So this gives me 60 franci is equal to 12 kilograms V final, or V final is equal to a positive 5 meters per second. 5 meters per second to the right. Now, the next part of this question asks me, is this collision elastic, inelastic, or maximally inelastic? And I'm finding as I talk to people a lot of confusion about those three. Let's make a table here. Energy, you know, that marker's just about, that's just about working. So, energy and momentum. So I've got an elastic collision, an inelastic collision, and a maximally inelastic. Now, for an elastic collision, is energy conserved? Mechanical energy, the type we've got formulas for, yes or no? Yes. Yes. Inelastic, it's not conserved. And maximally inelastic, it's not conserved. And they stick together. Now I know that after this collision, the little block is stopped and the big block's moving to the right at 5 meters per second. Can they be stuck together if they've got different velocities? No. And so that means it's got to be one of these two, elastic or inelastic. Now let's look at momentum. In an elastic collision, is momentum conserved, yes or no? Conserved. An inelastic collision, is momentum conserved or no? Conserved. In a maximally inelastic collision, conserved or no? Conserved. Conserved. Every collision. You cannot come up with a collision that does not conserve momentum. You cannot come up with a collision that will not conserve momentum. Now folks, sometimes what we do here in physics is kind of wishy-washy. You know, we use frictionless tables and we use massless strings and we make approximations, you know, ignore the air resistance. In a collision, momentum is conserved, full stop. I don't mean if you assume that there's no air resistance or you assume a frictionless floor or, no, in real life, momentum is conserved, okay? Momentum is conserved, even if there's explosives involved. Okay? It's always conserved. And that's why whenever we have a collision, we use momentum to solve that problem. Okay, so now, if I want to figure out what kind of collision this is, I have to figure out whether the energy is conserved. Well, before the collision, I have the little block moving at 20 meters per second, and that gives me 600 joules. After the collision, the little block stops and the big block is moving. It's got a mass of 12 kilograms and it's moving at 5 meters per second. And that's going to give me 150 joules. If those are different, if kinetic energy initial is not equal to kinetic energy final, then it's inelastic. There's not some test that you can just visually do to tell whether something is elastic or inelastic. You can tell if it's maximally elastic or not, but for the other two you just have to do the calculation. Did the kinetic energy stay the same or did it not? Now, yes, question? No. Just waving your hand. Okay. Now the next question on this problem asks, for how many seconds will block B, what's the friction force on the rough section of track? Well, finding a friction force we've known how to do for a long time. We draw a free body diagram. The weight force on that block is going to be 120 newtons. The normal force, therefore, is 120 newtons. That friction force is kinetic friction. That's going to be the mu sub k times the normal force. And that's going to give me 0.2 times 120 newtons, or 24 newtons. Now, this next part asks, how many seconds does the block scrape across that rough section? If I'm interested in seconds, in time, what kind of problem? Momentum. And so I use the, let me get myself some space here. It's not a collision anymore, it's a scraping. So I can't use momentum conservation. I have to use the general momentum equation, which is momentum initial is equal to momentum final, except when there's an impulse acting. So right as it starts scraping, I've got 12 kilograms moving at 5 meters per second, and then I've got a friction force of 24 newtons acting over some time, and I wait until it stops. And so that gives me 60 Franci minus 24 newtons. Delta T is equal to 0, or delta T is equal to 2.5 seconds. Now, if you have that problem on your exam, you see that the first part of it, before the collision, was energy. The collision part was momentum. If I asked for the time that it scrapes, that's momentum. But I could have asked how far does it scrape? And then it would have been energy. Okay? Now before I answer the last question, let's look at this problem again. This is the single boxcar coming in at 10 meters per second. It links up with the 5 boxcars, and we found that it went off at 2 meters per second. And we got that 2 by just conserving momentum. We had 5 times as much mass moving. It had to move 1/5 as fast. Now, what if the first car bounces? If it, instead of linking, it bounces, will this final velocity be greater than 2, equal to 2, or less than 2? Remember, it was 2 if it links. Will these 4 cars be going faster, the same, or slower? With your clicker, okay, let's see how we did. Oh, most of us got that right. It'd be greater. Okay, this was one of the biggest ideas in that tutorial last week. And that is that momentum's a vector. And because it's a vector, you can lose more than everything. Let's look at two situations. One where A links with the 4, and the other one where A bounces. If A links with the 4, it comes in with a certain momentum, and it links and still moves to the right, so A still has momentum to the right, just not as much. Now the change in momentum is what I have to add this long vector to turn it into a short vector. That's going to be the change in momentum for A. Now that's important because whatever change A has to the left, the 4 cars have the same change to the right. So that means I would have a change in momentum for the 4, the same size to the right. Now I know that because the change in momentum for the system of A and the 4 cars has to be 0. And in order for that to be 0, whatever change A has, the 4 cars have to have the same change, but in the opposite direction. So when I add them together, I get 0. Now, let's look at the case of A bouncing. I have the same initial momentum for A, but now the final momentum is to the left. And I put those tail to tail because I'm looking for the difference between them. The change vector is what I have to add to this one to bring it all the way down to 0 and out the other way. And that means if I got a bigger change for A, I'm going to have a bigger change for the 4. And so that means they will be going faster. Now you remember in that tutorial, student 1, and you should have been nervous that it was student 1. Student 1 says, oh, well, you're always going to lose the most momentum when A stops, because you can't lose more than everything. That's not true with vectors or with credit cards. Quick story. Back when tech stocks were just booming, just going crazy, my wife was working for a doctor that was making much more money in the stock market than in his office. And he kept telling my wife, he said, you and Greg ought to get in on this. It's free money. I mean, it just keeps going up. And she said, you know, we don't have any money. Well, the next week, we each got an envelope from Discover, and Discover offered us $20,000. We could write ourselves a check, and we wouldn't have to pay it back for a year. No interest. Just free money. So that's what we did. We each wrote ourselves a check for $20,000. We took the $40,000, we put it into some of the most exciting tech stocks, and 2 weeks later, it all crashed and it was worthless. Did I lose everything? No, I lost more than everything. I didn't own that $40,000. And I tell you this story so that you can learn from my mistakes. Never bet with money you don't own. And never bet with money that you do own. Okay? That's the message that I want to share with you. Now, because vectors can go the other way, you can have a change in momentum that's bigger than the initial momentum. You can lose more than everything, okay, if it bounces. Okay. If I look at this problem where a young man catches a football, and we'll assume that he's on a skateboard with really, really good wheels, the very finest wheels, so fine we could consider them frictionless. And he catches that football, and the football causes him to start rolling up the hill. And if I were to ask you, how high does he get before he turns around and goes back down? Is that momentum or is that energy? Yeah, it's both. First of all, I've got a collision. And it's a maximally inelastic collision. They stick together. Okay? And so that means I can't use energy. In a collision, I should never use energy. So I conserve momentum to figure out how fast he and the football and the skateboard are going after the collision. Then I take that motion and think of it as kinetic energy. And as he goes up the frictionless ramp, that kinetic energy is transformed into gravitational energy. And so I would conserve energy after the collision. Now you had a problem like that for your homework. You had a pendulum bob that came swinging down on a Tarzan swing. That was energy. And then it hit a block. You had a collision. That was momentum. And I just want to say that during an exam, sometimes you're going to have to separate a problem into two problems. You know, what happens before the collision, what happens after the collision. Okay? Or during the collision. We've been talking about collisions in one dimension. They are so much more interesting in two dimensions. Now, what I want to show you today is that just like solving a two-dimensional kinematics problem like projectile motion was as simple as solving two one-dimensional problems, a two-dimensional collision problem is just as easy as solving two one-dimensional collision problems. I'm going to introduce this topic by taking us on a field trip. We go down to the hockey rink, and we've got these two hockey pucks on ice. And one's going north and one's going east. They're both regulation hockey pucks, with the exception that we've modified them a little bit. So that when they hit, they stick together and have a maximally elastic collision. So if I have these two hit and stick together, which direction are they going to go off at with your clicker, please? And leave your clicker out. We're going to do about 5 of these. Okay. Good. C is the correct answer. Now, suppose I replace one of the hockey pucks with a Mondo hockey puck. But they're both going the same speed. And now, which direction is going to be most likely after they stick together? I was going to say it's not rocket science, but yeah it is. Okay. Good, B is the right answer. Thank you very much. Okay, this time I go back to the regulation hockey pucks. This one's going fast to the east, this one's going slow to the north, and they stick together. Which direction is most likely the result? Okay. The answer is D. Good. One more time. This time I have a Mondo hockey puck going slow. I have a regulation hockey puck going fast. And the question is, what direction, which vector best represents the final velocity? A can't tell, B is B, C is C, D is D. So last time. Okay, that looks like all of us. Okay, you said C. The answer is A. And here's why. What you were thinking is, oh, that one's got a lot of mass, but not so much velocity. So when I multiply the lots of mass with the little velocity, it'll wash out. Well, my department head, it turns out, is taller than me. If we take the number that represents our heights, he wins. However, it turns out that I'm heavier than he is. If we take the number representing our weight, I win. Height, then multiply it by his weight, and we do the same thing for me. Are we going to get the same number? Not likely. Not likely. It's once in a blue moon you'll be lucky. Okay? So how do we solve these problems in 2 dimensions? We recognize that momentum conservation is a vector equation. That means it has to be true in the x direction and in the y direction. And when we conserve it in the x direction and the y direction, we get our answer. Now, before I go any further, I just want to point out that this is, like I said before, this is real physics. In 1995, a crazy person, Timothy McVeigh, blew up the Oklahoma City Federal Building. Now, authorities knew that it was a rental truck that had been parked, and then it had been filled with explosives, and it blew up. Now, they just didn't know who put it there. Now, the way they solved that mystery was with that equation right there. They assumed that the truck was parked, that he wasn't driving past, he wanted to get out of there. And so that meant that the initial momentum of the bomb was 0. 0. 0 in the x direction, 0 in the y direction. That means that after the explosion, no matter how messy, the momentum of that truck had to be 0 for all parts of the truck. So they went and they gathered all the parts of the truck, and they found a part there, and they figured out how fast it had to be going to get there. They found a part there, and they figured out how fast it had to be going to get there. When they added up all the momentum of the truck after the explosion, it didn't add up to 0. There was momentum missing that direction. So they went that way, and they found a piece of the axle which had the serial number on it, which led them back to the company that rented the truck, which told them who rented it. And that's how they captured Timothy McVeigh. This is real physics that works in everyday life. And that's also the way rocket science works. Okay, so it's all on conservation of momentum. Now, here's a problem in 2 dimensions. I'm going to say 2 things first about this problem before I solve it. First of all 2-dimensional collision problems will be solved the same way I solved this one. Secondly, this problem's a little bit more messy than what I would ask you to do on an exam. So if you can follow what I'm doing on this problem, you're going to be fine. Okay? Now what we have is a small car going 15 meters per second, and it collides with a large truck that's just lumbering along at 5 meters per second. The car is going due east. The truck is going 37 degrees north of east. They collide and lock bumpers, becoming a very, very ugly truck bogle with 22 wheels. Okay? And the question is, how fast and in what direction are they moving right after the collision? Right after the collision. Don't wait until they screech to a halt and call the cops and he hit me, no, she hit me. It's right after the collision. So, let's solve this. I'm going to need two boards. So I solved this by saying P initial equals P final. And by initial I mean right before the collision, by final I mean right after, and by P I mean the P of the system. The system containing both the Volvo and the truck. It's a vector equation, so I'm going to need a coordinate system. We'll call this the positive y direction, this the positive x direction. Now the car has momentum equal to 2,000 times 15, or 30,000, what? What are the units? France, I just wanted to hear you say that. Makes me happy. Okay? Now, the truck has momentum 8,000 times 5. That's going to be 40,000 France, I. Now, what I want is the momentum of the system. If the car has 30,000 France, I, and the truck has 40,000 francs, how many francs does the system containing both the truck and the car have? You're tempted to say 70,000, aren't you? Yeah, and I've been giving exams a long time. And when I give this problem on the exam, half of you say 70,000. And you get 0 points. I'm so sorry. That's how you add up money, that's how you add up energy, that's how you add up any scalar. But this is a vector. This isn't 30,000. This is 30,000 east. And this isn't 40,000. This is 40,000 at 37 degrees north of east. If I want to add these as vectors, I'm going to need that same table that I had in two-dimensional motion with the x part and the y part. Now if I look at the car, this momentum is all in the positive x direction. All 30,000 francs are in the positive x direction. But if I take this truck momentum, some of that is in the positive x direction, some of it is in the positive y direction. Now if I use the fact that this is a 3, 4, 5 triangle, well this is 5 times 8,000, so this must be 3 times 8,000, and this is 4 times 8,000. Now if you'd rather use 40,000 francs times the sine of 37 degrees, you can do that too. Either way, you're going to get 24,000 in the y direction and 32,000 in the positive x direction. Now, I can add these up to get the momentum of the system. I add this up and I get a positive 62,000. And I add that up and I get a positive 24,000. Now, what that means is that when I look at the momentum of the system, it has an x part that is 62,000. It has a y part that's 24,000. And that means that the actual momentum of the system is going to be 62,000 squared plus 24,000 squared square root, and that's going to be 66,500 francs. Now this angle here, that angle is going to be the inverse tangent of the opposite side, 24,000, over the adjacent side. And that's going to give me 21 degrees. So, that means the momentum of the system is equal to 66,500 franci at 21 degrees north of east. Now, did I just calculate the momentum of the system before the collision or the momentum of the system after the collision? Both. That's the point. That's the thing that's so critical, is that that stays the same. Now, here's the confusing part. Before the collision, there's nothing in the problem that's going in a direction 21 degrees north of south. Nothing we can see with our eyes. There is something called the center of mass, which is moving along in a direction of 21 degrees north of east. And we've talked about that a little bit in tutorial. We're going to talk about it some more later in the semester. But after the collision, when they're locked together, when they're moving as one, if their total momentum is headed 21 degrees north of east, so are they. And they're moving at the same speed because they're locked together. Now normally, the momentum of the system would be the momentum of the car plus the momentum of the truck as vectors. But when they're moving together all as one, I can write this as just the total mass times the final velocity. And that's what I'm looking for, is the final velocity. So if I write P system as 66,500 franci at 21 degrees north of east, and that's equal to the total mass, 2,000 plus 8,000 is 10,000 kilograms, V final. I solve for V final just by dividing both sides by 10,000, and I get V final is equal to 6.65 meters per second at 21 degrees north of east. Talk to your neighbor. See if your neighbor understood that problem. Are there questions on that? Let me show you another one that involves traffic. This is the problem that's on the back of your exam preparation sheet. I have an SUV of 600 kilograms approaching an intersection at some unknown speed. I have a car of mass 400 kilograms approaching the same intersection going north at some unknown speed. Now, we know that the speed limit in this neighborhood is 30 meters per second. When you think about that, that's a little more than 60 miles an hour. The people in this neighborhood don't love their kids that much. But we find that when they crash and lock together, that they scrape across the pavement, they leave skid marks that are going 53 degrees north of east. And if you measure those skid marks and you use what you know about the road, you can figure out that right after the collision, they were scraping along at 20 meters per second. Now the police call you in because you're the physicist, the rocket scientist, and they say, who was speeding? Who do we give the ticket to? Let's solve that problem. Well, if I use my table where I separate out the x part from the y part, car A has momentum that is all in the x direction, the positive x direction, and it's going to be 600 kilograms times VA. None of it in the y direction. If we look at car B, all of its momentum before the collision is in the y direction, none of it in the x direction, and it would be 400 kilograms VB. Now, when I add this up, I get 600 kilograms VA for the system, and I get 400 kilograms VB in the y direction. But I know that this momentum is the same before and after the collision. And after the collision, they're all moving together, so I can use this equation. So that means that the momentum is going to be, I've got 600 and 400, that's 1,000 kilograms times 20 meters per second at 53 degrees north of east. So that means that my total momentum of the system is going to be 20,000 franci at 53 degrees. Now I can break that up into an x part, a positive x part, and a positive y part. This is a 3, 4, 5 triangle. And you can see from this side that the thing that I'm multiplying by is 4,000. So that means this is going to be 16,000, and this is going to be 12,000 franci. So this has to equal 12,000 franci. How fast was A going? This has to equal that. It's going 20. This has to equal the y part of 16,000. How big is VB? 40. More than 80 miles an hour. Throw him in the pokey. Okay? Clearly he was speeding. Questions on how to solve those problems?
Is this actually what they do during,
What's that?
is this actually how they solve collision issues when the drivers
You're going to have to say that again. I was distracted.
Is this actually what they do so that the navigator into your
Oh. If the question on the exam is that kind of a question, you mean? Oh, yes. Actually, the person that had my job before I got it was making so much money going to trial. Lawyers were hiring him to go and use this basic conservation of momentum to figure out, based on the skid marks, who was speeding and who they should give the ticket to. In that case, it was not just the ticket, but it was also the $2 million settlement involved. Did that answer your question? Costco called this afternoon and says I can go pick up my hearing aids. They were broken. So on Monday I'll be able to hear you. Have a good weekend, folks. Happy Easter.
Studying physics is hard enough, but doing it from home on your own because of this COVID thing makes it far more challenging. So to help you through this, the physics department has created a virtual help center. We have grad students, TAs, student assistants, and instructors standing by from 8 in the morning until 6 in the evening, Monday through Friday. To sign up for the Virtual Help Center, you will need to download Microsoft Teams, which is free to MSU students. The link to do this is listed on the D2L post under the announcements, and so you will register for Teams using your NetID at msu.montana.edu as your username. Then you enter a code provided on your D2L announcement that is specific to your class. If you've already registered to be part of Teams for your tutorial, you can enter the class code to use the Virtual Help Center. When you visit the Virtual Help Center, you enter the general room. Type something in the thread like, "Hey, can I get some help?" and a staff person will respond, perhaps by text, but if it's more complicated, and let's face it, physics is complicated, we can initiate a video call. Our staff can use a number of different tools like a whiteboard and a webcam to help you out. So please, we may have to do this social distancing, but our staff is here and is virtually available for you Monday through Friday from 8 in the morning till 6 in the evening. And we want to try to make this experience less bad. So if you have any questions, you can call or text me, Tom Woods, your Student Success Coordinator, at 406-850-4461. That's all, folks.